All right, let's continue along in chapter 13 in kinetics, and let us consider integrated rate laws. Then we are going to answer the question of either A, how much is left at some point in time, or how long will it take? So we're going to look at three different types. We're going to look at zero order, and in fact, we're just going to kind of introduce zero order, and then we're going to proceed to ignore it. In zero order, rate is equal to k times a to the zero, and we'll consider that briefly. We're going to spend a lot more time on first order. First order's got very doable math. And when we do this, we have rate is equal to k times the first order. And on second order, we're going to have rate is equal to k times a squared. Now, we're not going to do two reactants. We're going to stick to one reactant. And so all of these are going to be some form of A goes into B. So what do we have? Well, we know the rate is going to be, and because we're looking only at reactants, is going to be the negative change in concentration of A with respect to time. And for zero order here, that's going to equal K times A to the zero. Well, A to the zero almost doesn't matter here because it's going to be anything to the zero is 1. But if we integrate this and we look at from time 0 to some point in time t, we're going to get this equation right here. What does this tell us? First of all, this is a straight line equation. This is linear. And it says that if we have y is equal to mx plus b, we're going to have that the concentration of A at some time is equal to minus kt plus the initial concentration here at A naught. So if we graphed this and we put A over here and we put time t over here, we get a straight line with an intercept of A naught. Now, only if we get a straight line does it tell us that this is a zero order reaction. So what do? We collect our concentrations over time, we graph it, and see what kind of shape we get. So the first one is 0. A plot of A versus time giving us a straight line is going to be zero order kinetics. Now, much more interesting is first order. First of all nuclear decay. Anytime we have nuclear decay, it is inherently first order. First order means that our rate, minus change in concentration of A over change in time, is equal to K times A to the 1. If we integrate this and put it in a straight line form, we can get a line of the form y is equal to mx plus b, telling us that if we plot the natural log of our concentration versus time, we're going to get, and we get a straight line. The intercept, it's going to be the natural log of A naught. The slope here is minus k. And if we have this data, and again, we're going to collect A and time, and we take the natural log and plot it versus time, and we get a straight line, then we know we have first order kinetics. We're going to have two equations for this. One of them is the linear form, but in general, we want an equation that we can work with nice and easily, and this is the standard form we're going to work with when we do our problems. First of all, how would you figure this out? You go to the lab, you collect data. You get concentration versus time. And you first try, and you would try A versus time. Pretend it's 0, and it doesn't work, and it's not a straight line. Then you keep trying different forms to try to get something that works. So again, how do you know it's first order? Because a plot of the natural log of A versus time will be straight. Your plot would look something like this. The decomposition of hydrogen peroxide is first order. If we plotted the same data where we had A versus time, we would get a different shape and it wouldn't be a line. And if it's not a line, then this plot doesn't work and you're going to keep plotting. All right, what about second order kinetics? Well, it's still going to be of the form A goes into products, except for now rate is going to equal K times A squared. Our rate's going to be the same. Our rate is going to be negative change in concentration of A over the change in time, and we're going to integrate it. And when we integrate this, we're going to get this equation right here, where 1 over concentration of A sub t. Now note A sub t is what's left, is equal to Kt plus 1 over the initial concentration. And If we look at this and we consider this, this is inherently a straight line form. This is y is equal to mx plus b. And if a plot like this gives you a straight line, you know you have second order kinetics. So if we look at this reaction here of C4H6, and we consider, first of all, plotting the natural log of the reactants versus 1 over the reactants, we notice that if we plot the natural log, this is not a straight line. Because this is not linear, it means that our plot doesn't work, and we are going to be not first order. So we go and we try second order. We plot 1 over the concentration versus time. We get a straight line. Therefore, it is a second order plot, and we have second order kinetics. Remembering that kinetics is almost always going to be experimental, and we have to go to the lab to figure out what we're doing. So to sum up our kinetics and our equations, we're going to have 0, 1, and 0 first and second order. Our rate law is going to be, our rate is equal to k, and remember this one is a to the 0. This is going to be our integrated rate law. For here, our first order, our integrated rate law, these have the t missing, but this just means at what's ever left at time t. And we have one more thing we need to consider, and we need to consider the half-life. Half-life is by definition how long it takes for 1/2 of the sample to decay or react. So how long it takes for 1/2 of the sample to react. That is going to be our half-life. The really interesting thing is when we go to first order, our half-life does not depend on the concentration. Notice here in second order, our half-life depends on what we have. Same here on this one. Here, there's no concentration. When you have first order kinetics, it doesn't matter how much you have, it takes the same amount of time for half of it to react. You can plug this in and show to yourself that for a first order process, the half-life does not depend on A naught, but here are going to be our equations. We're going to say to either t to the 1/2 is equal to the natural log of 2 over k, or k is equal to the natural log of 2 over t to the 1/2. Well, what's k? K, again, is that rate constant that we saw from the rate law. It is going to depend on the half-life. Let's consider what that means. All right, I'm looking at cobalt-60. Cobalt-60 has a half-life of 5.27 years, which means if I start out, let's say, with 10 grams, and I let it react or decay for 5.27 years, I'm going to have 5 grams left. If I let it decay for another 5.27 years, our rate doesn't change. It's still going to decay the same amount. It's going to go down by 1/2. 1/2 of 5 is 2.50, and we'll continue to just do like that. This is interesting and very interesting when you stop and you consider nuclear decay from something like Chernobyl or the Fukuyama power plant that was damaged in the tsunami, and you look at what you have in that plant. Everything you have in your nuclear power plant is going to undergo nuclear decay, which says if you've got a kilogram of a sample that takes 100 years to decay, after 100 years, you're going to have half a kilogram. If you've got 1 kilogram of a sample that takes 1 billion years to decay, after 1 billion years, you're going to have half. After 2 billion years, you're going to have 1/4. How much you have or how long it takes does not depend on the concentration. Okay, half-life is half-life. So let's consider a nice decay of cobalt-60. So cobalt-60, which has a half-life of 5.27 years, we want to know, first of all, what is the rate constant? Now, why do we want to know the rate constant? We want to know the rate constant because our equation is not in half-life. Our equation is natural log of a sub t is what's left, over a naught is the original, is equal to minus kt. T is how long, a sub t is what's left, a naught what's original. So this is a naught, We want to know what remains after 25 years. That is T, and we're going to solve for A sub T. Now, to solve for A sub T, in order to do this, we have to get K first. Well, K is the natural log of 2 over T, the 1/2. And when you plug that into your calculator, you're going to get a K is equal to 0.132 because the half-life is in years. This is per year. And now we just plug. The natural log of A sub T over A naught, which is 2.5 milligrams. It makes no difference what units you use. Whatever units you start with or what the units are going to be when you end off for your concentration, equal to 0.132 per year. Make sure these units, though, are the same, multiplied by 25 years. This is math, and we're just going to plug that in. And when we plug that value in, we're going to get equals minus 3.29. Our years cancel. On this side, we'll get the natural log of A sub T over 2.5 milligrams. And we're going to remember here that we need to get rid of the natural log. To do that, we're going to exponentiate both sides. The exponential of the natural log is going to give us A sub T over 2.5. E of minus 3.29 works out to be equal to 0.037. And we're going to find out that A sub T is equal to 0.0933 milligrams. Note A sub T is always what's left. All right, let's just do another one. We liked half-lives, by the way, because half-lives kind of make sense to us. If we have a sample here of the SOCl2 with a half-life of 245 minutes, we know that if we let it react for 245 minutes, we'll go down to 50%. If we react for another 245 minutes, it will go down to 25%. And another 245 minutes will go down to 12%. So we can kind of wing our way through this to figure out how much we have. But here, we're just going to plug it in and do the math. So we have that T to the 1/2 is equal to 245 minutes. We know that K is equal to the natural log of 2 over the half-life, which is 245 minutes. And K is equal to 0.00283 units of per minute. Now note K comes out the same units as you start out with the T to 1/2. So for our equation, 1/10 tells us that what's left. So if A sub T is 1/10, so that's going to be our 0.1 if A naught is equal to 1, or you could equally say A sub T is equal to 10%, A naught is equal to 100, whatever it makes sense to you to look at these values. 1/10 of what we have to begin with. We'll plug it in. The natural log of 10 over 100, that makes sense to me out of 1/10, is equal to minus 0.00283 units of per minute. Now we're solving for T. This stuff is going to be a number. We're going to divide through by that number, and we're going to get that our time T is equal to 814 minutes. Make sure that makes sense. If we start out and we go from 100% to 50%, that's 245 minutes. If we want to go down to 25%, that's another 245. If we want to go down to 12.5%, that's another 245, plus a little. We take and we work those out, we're going to get 245 times 3, which is 735, plus a little, will probably tell us that we've got about 800 minutes, which at least tells us that we're on the right track. Using the equation gets us to be a bit more precise. All right, so what can we use this for? Well, one of the things we use this for is dating, finding out how old things are. One of the things we use to date with is carbon-14, and we use carbon-14 to date organic substances. Now, everything is limited by how much of the material you have left in it. So everything has a certain lifetime that these are usable for. But for right now, carbon-14 has a half-life of 5,730 years. And we can date stuff up to about 25 or 30,000 years old with this. What happens? A neutron up in the upper atmosphere hits nitrogen and it turns it into carbon-14. Carbon-14 is radioactive. It will decay with a half-life of 5,730 years into carbon-12. So what do we look at? We look at the ratio of carbon-14 to carbon-12 in the sample to see how old it is. The newer it is, the more carbon-14 we have, and the older it is, the less carbon-14 we have. So know at some point, if it's alive, it's going to be constant. And we have a certain amount of carbon-14. But as soon as the organism dies, it doesn't take any carbon-14 in anymore, and the carbon-14 begins to decay. How could we use this? So this is a sample of the Dead Sea Scrolls. The Dead Sea Scrolls are made of papyrus. Now, papyrus is organic, which means we can date it using carbon-14. Because it's a plant and it's going to intake carbon dioxide, it has a steady stream of carbon in it until it dies. And after it dies, the carbon in it starts to decay. And this carbon-14 is going to decay with a half-life of 5,730 years. So the question is, if we know how much carbon-14 is in there compared to a fresh sample or compared to the carbon-12, we can get a pretty good idea of how old this is. So some data. Here's what we found. We found that the ratio of carbon-14 to carbon-12 is 0.795 times that what was found in plants living today. What does this tell us? It tells us that concentration of carbon-14 now, which is our A sub T, is equal to 0.795, and the concentration of carbon-14 original would be a value of 1. We know that the half-life is 5,730 years, and we know our equation is a natural log of A sub T, what's left, over A naught, which is original, is equal to minus A T, and we know that our K is a natural log of 2 over T to the 1/2. If we plug in 5730, we're going to get a K value for our carbon-14 of 1.21 times 10 to the minus 4 per year. And our equation, natural log of 0.795, what's left over 1, is equal to minus 1.21 times 10 to the minus 4 per year multiplied by time. If we solve for the time, we're going to get about 19,000 years, which tells us is that we know these were built or written around the time of the death of Christ, is about consistent, and they're about as old as we think they are. All right, last thing we're going to consider. Last thing we're going to consider is second order. First order, remember all nuclear decay is first order, but second order, we're going to have to go to the lab and figure that out. And this is going to be interestingly time dependent. So please note that the half-life for second order kinetics is going to equal 1 divided by K times A naught. And what you find with second order kinetics is the half-life doubles every half-life. So in this case, if our first half-life, which we can solve for, is a certain value, then the next half-life would be double that one. It takes longer for these things to come together and react. Now, be all that as it may, this is plug and chug and it's easy to do. If we want our initial concentration, which is this guy, is 1 over 0.025 molar, is equal to 1 over the original concentration, 0.002 molar. Remember, this is what's left, plus our K value of 1.0 times 10 to the minus 3 per molar second multiplied by time. And this is just math. We're going to take our 1 over 0.025, we're going to subtract 1 over 0.2, we're going to divide by our K value, and we're going to find that the time that this is going to require is equal to 35,000. Our units are molar per second, so this is going to be units of seconds. What is the half-life? We can do the math and calculate the half-life because t to the 1/2 is equal to Rk 1.0 times 10 to the minus 3, or 1 divided by 1.0 times 10 to the minus 3 multiplied by 0.2, and we get a half-life for this specific time in this reaction of 5,000 seconds. Second half-life would be double that value. All right, that is the integrated rate law. How long or how much is left?